All right, good deal. So it sounds like we've got some questions about this combinatorial assignment. Oh, where's all my pens? I forgot to get prepared on my pens here.
Cut that.
Okay, so I think you had, what, 4 problems?
Yeah.
Okay.
Can I ask a question on everyone?
You can ask me a question. I'm not saying that I'm not going to do it for you, but
Okay, I'm more concerned about the 1613.
Yeah.
I have a question. It's like, because do you have,
on 1613, yeah.
so,
I didn't bring my book.
Trouble problem.
Do you want my
You
book?
have 2 bags.
No, that's fine. Just tell me what the problem is. You got 2 bags?
And it wants to know what are the chances you're going to draw a red and then a black ball in each bag.
But you have 2 different bags.
Right.
I'm getting my book right.
So the first bag has a red, black, and a white.
The first bag has a red, black, and a white.
The second bag has a red, black, green, and a white.
A red, black, green, and
And
white.
it wants to know, no matter what bag you choose, what are the chances that you draw a red and then a black.
Yeah, that's okay. And what are the chances that you draw a red, then a black? Well, I mean, see, once a bag is chosen, there's only one way to select first a red and then a black.
Right.
Are you with me on that?
Right.
Okay, so what you do is you calculate, I think what you do is you calculate the 2 permutations of the first bag, right? Well, what you have to do is you have to calculate
Total, everything, and then you subtract 2.
how many different ways are there to select first one ball and then another. Yes, it is going to, yes.
So you have 2 changes.
Yeah, it's going to be 2, you're right, right.
But what I want
Yes,
you
yes.
have to add 2. So you have 2, and then
It's
the
going to be 2
permutation of
over.
one bag, and then plus the permutation of another bag.
Yeah.
Oh, you don't select 2 balls. You just pick them all out, but a red and a black have to be next to each other.
Well, when you're counting everything, we're not saying that you only have to pick a red and black. I'm saying you can do anything.
As long as it's red then black.
On the 1646.
On 1646, yeah, there were like 4 parts to that.
Right. Now, do we add them?
Well, you know, we did, remember this one that we did with the committees?
We added them.
I think if you remember last time, actually, I had a solution where you did all the ones and then you subtracted the ones that you didn't follow that category. But on the other hand, Ben said, well, why don't you just add the ones that are in that? And we got the same answer. So, you know, there's more than one way to skin a cat, as my father-in-law used to say. There's 2 ways to skin a cat.
So like on the
Anyway.
it says, how many committees of 2 men and 2 women can be formed?
Are you talking part A?
Part D.
Part D.
Oh, part D. Oh, that one. Oh, I'm sorry. We were doing part D. I didn't realize we were doing part D. Oh, yeah. In this one, there's not an adding or subtracting. It's what? Because it said, what did it say? It said what? And how many ways can you do what?
Pick 2 men and 2 women. A committee.
For every 2 women you pick, you can pick 2 men of
Yes.
a different amount of ways.
Yes.
But say like on A through C, those ones we've added.
Or subtracted.
Yeah, I subtracted. I got the total and subtracted the ones that were not in that
Do you want us to do all the
category.
math, or can we just leave it as?
It would be nice. I mean, you guys have calculators with choose buttons. Why don't you give me a number?
We do.
You should know how to do your choose. But for part D, it is correct that what you do is you multiply, because for each one, because it's an ordered pair of a man and a woman.
That probably doesn't explain it at all.
Well, that makes sense. I just don't know in the other ones if I add them.
Well, like I say, there's more than one way to do it. You can either add, I mean, the way I did it is I subtracted. I did the total, and then I subtracted the ones that had to be excluded.
Which is really easy for A.
Yeah, I think sometimes, yeah, the number of calculations that you would have to do otherwise gets, you can minimize the number of
Well,
calculations.
how would you do it doing the total and subtracting?
For A, you take, like.
Well, now, don't give her,
all of them.
don't just give the answer.
At least one man, you have to think of the cases that aren't there,
Yeah,
which would mean that they're all women. And so
Yes.
you take away the cases
where they're all women. Yeah, you subtract you do all the cases, and then you subtract the cases for which they're all women. Okay?
So I'm still confused on 1613.
2 divided by,
It's 2 divided by some number.
Same for the bags then? For 2 different bags?
Well, the question is, how many different ways are there to select first one ball and then another?
4 choose 2, and then plus 3 choose 2? Oh, no.
No, I don't think so. No, I don't, no, yeah, no. Yeah, I don't think it's 4 choose 2. I'm going to let you chew on this one. I don't want to do your homework for you.
The problem is this, each bag has different number of balls in it.
Right,
That's what makes it hard.
right,
Otherwise,
right. There are 2 ways, one for each bag.
yeah, well, that's fine.
Wait, there's 2 different answers then?
No,
There are 2 ways to get a red and a black.
yes.
I bet. Okay, relax.
I'm getting so confused.
That's why this is a good problem.
Wait, that is right, isn't it? Because if you choose the second bag, then there's 4 choose. Oh, it is automatic for this?
Yeah, you have to choose red then black.
Yeah,
But you're just calculating the total right now.
Because the chances for.
Okay,
like,
so you
in
got
one bag is-
permutation 4-2 plus permutation 3-2. Because if you happen to select the first bag, well, the first bag, then it's 3-2, and if you happen to choose the
Okay.
second bag, it's 4-2.
okay, well, I'm not going to say anything, but, I mean, it sounds like we're doing this kind of as a group project, huh? Well, we're not doing chances. I mean, when you say chance, notice that this problem is,
If you happen to choose to take the
But
first
wouldn't that
bag,
give you the
No,
fraction of the cases?
well, no, yeah, notice that this problem is asking for a fraction, and there's no concept of probability in this chapter at all. It's just counting. But if you,
well,
you
combination would be
know,
like,
but you're right, this has application to probability, and you could frame it in terms of chance, you know, if it was a random. Okay, let's move on, all right? We had talked about these definitions, the definition of a degree of a vertex, and here's a theorem: the sum of the degrees of the vertices of a digraph or multigraph equals 2 times the number of edges. And then we also discussed 19.4, in a digraph or multigraph, the number of vertices of odd degree is even. And there's exactly what that means. And now what we want to do is 19.4.1, a definition. A path has the following properties. So A, B, and C are a definition of a path. Now, to do this, to illustrate this definition of a path, I want to go back and do this, put this digraph up that we did before. We had a digraph that looked like this. And this is A, B, C, D, E. All right, so here's our digraph example from last time. And now, with this digraph example, and with this, what is 19.4.1, let's see what the definition of a path is. Okay, first of all, a path starts with a vertex, ends with a vertex, and alternates between vertices and edges. Okay? So it starts with a vertex, ends with another, possibly another vertex, and alternates between vertices and edges. So each directed edge in a path is preceded by its start vertex and followed by its end vertex. An undirected edge is preceded by one of its vertices and followed by the other. Okay, so what this tells you is that you can't just like have B and then have edge ED and then have C. You can't do that. Instead, what this says, each directed path is preceded by its start vertex, so that if the start vertex is B, then it's followed by its end vertex C. So the edge then it would be B and then the edge BC and then the vertex C. And furthermore, part C says no edge appears more than once. So let me give you an example of a path. Here's an example of a path. First of all, it's an ordered tuple, right? And it starts with a vertex. I'm just going to arbitrarily, for this example, we're going to start with the vertex B. Are you with me? And then it alternates between vertices and edges. So here's a vertex. The next thing that I need is an edge, right? But it can't just be any old edge. You know, I can't just use the edge ED here. Why not? Because it says what? An edge is preceded by its start vertex. So this edge has to be an edge that starts at B. Are you with me? So let's just say that it's B, edge BC. Yeah? And then what? And, yeah, this has to be C. So here's vertex, edge, vertex, edge, vertex, edge. Okay, you see what I'm saying? And so it's B, here's an example, B, B, C, C, and then this next one could be C, E, and then the next vertex has to be E, and then, yeah, EC, right, and it has to end on a vertex, so let's say C, so boom. So everybody see that this is an example using that strict definition of a path. And furthermore, we have BC, CE, and EC, and we haven't repeated these edges. These edges don't appear more than once. So you see what this actually looks like. I mean, you can just think of it. You can think of this as being a map, right? And it's like you start at B, you go along this edge to C, and then what do you do? And then we come along this edge and we go to E, and then E, and then here we're going to come back and we wind up here. So that's kind of like our path.
Technically, you could go from E to D though.
Well, you could, but this is just an example. Yeah. Are you with me? Now, what we're going to do is we're going to use we frequently will use a short notation because, you know, here we got B, B, C, C. So, you know, short, when possible, we'll do a short notation. And we'll just call this B, C, E, C. All right? Leave out the edges. Are you with me? So that's a short notation. Now let me ask you about this. Well, let me give you an example of something that's not a path. Not a path would be B, BC, C, CE, E, oops, CE, vertex E, EC, C, CE, E. Now why isn't this a path? This is not a path. Why is this not a path? Yeah.
It would become a loop.
Well, it's just not a path. That's why it's not a path. Are we good?
Totally.
Okay, now these multigraphs are really interesting. There's an interesting history, actually. Have you guys heard of Euler? Okay. Yeah, Euler is a famous mathematician, German, and I think this was in Prussia. There was a town in Prussia called Königsberg, And these are the Königsberg bridges. I'm going to draw you a map. So here's in the town of Königsberg. There's a river that goes through the river that goes through the town, and there's a fork in the river. So it actually goes like this. Okay, and so there's a fork. So there's a land mass here and a land mass here, and not only that, but there's an island. There's an island here. So does everybody see where, here, we get blue for the water. Little waves, okay. All right. And the thing of it is that there's 7 bridges. There's the 7 bridges of Königsberg. Well, so what the villagers had done is they had built a bridge. They had built a bridge here, 2 bridges to the island on this side, 2 bridges on the island on this side, and then they had a bridge here across the river here and a bridge across the river here. Are you with me? And then they also built a bridge from the island to this landmass. So that's the map, right? So there are 7 bridges. All right. And let me tell you what the people of Königsberg did. On Sunday afternoon, I'm making up a few of these details. They would like to go for the they would like no, this is real. No, this actually no, the map and the problem is real. Sunday I'm not too sure about. But anyway, people would like to go for a stroll on Sunday, and what they would like and they would like to stroll around the town of Königsberg. And so a citizen would step outside of his house and take a walk across the bridges. And here's the question that the people of Königsberg had: is it possible to start at one house on one of the land masses and cross each bridge exactly one time and return to the house?
Yes.
I doubt they're really boring.
Doesn't matter which landmass you start on?
Right.
Can you do it from any landmass? Is that what they're asking?
Yes.
Oh, you can start on any landmass?
Yes, as long as you come back to the same one and cross each bridge exactly one time. Because they were still I haven't crossed this bridge. Oh, I crossed this bridge. Oh, wait, I want to cross that bridge. I don't want to cross the same bridge twice. That's the question.
It is impossible because they all have odd numbers.
You. Well, yeah. So you jumped the gun. Now, if you had lived back then, maybe you could have been Euler.
It's been like, no.
But okay, so Euler, they asked him this, and he puzzled about this, and of course nobody believed that you could. And as you have maybe did with trial and error on this figure, he invented graph theory from this problem, and he proved that in fact you cannot do it. All right. And how did he do this? What he did is he modeled this as a graph. Now, so if you
4 points.
yeah. Now, what are but now in a graph you've got vertices and edges. So which ones are the vertices and which ones are the edges? Yeah, the land masses, right. So here, if we call this land mass A, and this one B, and this one C, and this one D, and then if we number the bridges, 1, 2, 3, 4, 5, 6, and 7, then what would our this would be a multigraph, would it not?
Yes.
Remember the definition of a multigraph. So what would it be? It would look like this. So here would be A, D, and C, right? And this would be B. So here is A, D, C, and this one's B. And then our graph would look like what? Our multigraph would look like what?
There would be 2 lines from A to D. A line from A to B.
2 from
Yes?
One from D to B.
One from D to B.
That's a good example of like the unordered days.
One from D to B.
One from D to B. Yeah? Are we good? So Euler, he modeled it like this, and then we could, and then, here we have one, this would be 1, 2, 3, 4, 5, 6, and 7. And what would a path be? What would an example of a path be in this? It would be like, could be like A6, B5, D1, A, something like that. Just as an example. Are you with me?
Does a path have to end backwards?
No, it doesn't. But actually can it?
You can't
Can
use
it?
the same edge twice.
It can't, can it, according to the definition of a path.
Yes.
And vertex.
It's okay to have the only thing that can't be repeated is a what? Is an edge. But vertices can be repeated. Yeah? So so let's come back to this, and your observation was correct, and even for the right reason, so.
On that graph you just erased,
Oh, shoot, I wish I hadn't erased it.
can you have a path B, 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 B then?
Actually, I should not have erased it because I'm going to do that example again. So let me redraw it, sorry. B, edge, BB. Yeah, that's a path. Yeah. Now, let's take a look. We have, in 19.4.2, we have some definitions. We have a simple, we have the definition of a simple path, a cycle, connected, an undirected, connected for an undirected multigraph, and connected for a digraph. Okay, so these are 4 different definitions. All right. So let's take a look. Let's first of all take a look at the definition of a simple path. A simple path is a path in which no vertex appears more than once, except that the first and last vertices may be the same. Okay, so that's a simple path. So let's think about this path right here. Is this a simple path? Does everybody agree? Okay, so this is a simple path.
Also a cycle, right?
Ooh. And let's take a look at the definition of a cycle. A cycle is a path with at least one edge and with the first and last vertices the same. So this is a simple path. This is also a cycle.
Path can be a cycle.
Okay, so is everybody clear on that? On the definition of a simple path and a cycle?
Question about
Can a cycle have a vertex other than the beginning and the end appear at the same time?
Yes, because a path can.
So then it's not always, no, a path can't repeat vertexes except for the end.
No, a simple path.
Right, a simple path, that's what I meant.
Oh, sorry, I misunderstood you.
Is a
Say-
cycle always a simple path? Or because a cycle, according to that definition, can repeat vertices?
A cycle is a path with at least one edge and with the first and last. No, a cycle can be not simple. It may or may not be simple. Am I right about that?
You're right. We made a mistake. I have a question about cycle though.
A
It's
cycle.
a path with at least one edge.
Uh-huh.
Are there ever paths without an edge?
Well, yeah, it's the empty path. I mean, it's just.
The empty path.
Yeah, well, it's the empty case.
Okay, so like.
So it would just be.
a vertex.
It would just be a vertex. So in order for it to be, so we don't want to count that as a cycle. All right. Okay, so check this out. What about here? Here it is. Here's the empty one. Is this a simple path?
Yeah.
I'm talking about this one now. Is this a simple path? Now this is a digraph. That's a multigraph.
No, a simple
Right,
path
this-
doesn't have to have an edge, so
So is this a simple path? Okay, this is a simple path. And maybe this will clarify it. How about this? BB. Now I'm doing the short notation. I'm not,
Yes, it is.
Is this a simple path?
yeah.
Okay, how about BCED? BCED. D. Is that a simple path?
Yeah.
Is everybody following this all right?
Yeah.
How about CEC? Is that a simple path?
Yes.
Yeah, that's still a simple path. Does everybody see why? It follows it.
Same reason BB is.
Okay, how about BCEC?
No.
Yeah, this one is not a simple path. All right. Are you with me? Okay. Now, let's see if, now watch this. This is an interesting theorem. See if you can understand this. If a graph has a path from vertex B to vertex C, then it has a simple path from B to C. This is an existence theorem. If there exists a path from vertex B to vertex C, then there exists a simple path. But wait a minute. How can that be? Here's a 19.6 example.
To get from B to C, repetition is never necessary.
Well, I mean,
It could be a part, it could be a part of the
if
path
the
that
C,
you could cut all the repetition out and get just from B to C.
yeah. Okay, so here we go. Let's look at this. First of all, is this a let me ask you this. Is this a simple path? A, B, C, D, E, C,
No.
F, G.
How does A get anywhere?
It's not on that graph.
Oh, sorry.
Don't worry about it.
No, that's not, this is not a good, oh wait, am I talking about,
There's only 4 variables over there.
We don't need.
wait, exactly, what am I talking about here?
Draw a new picture.
Do I need to draw a new picture? A, B, C, D? No. My notes are wrong. Let me go. Yeah, what's going on here?
I think there's a new picture.
I don't think we need to see the picture.
Oh, actually, yeah, this is not a picture. Yeah, right. We don't need to see a picture. Yeah. So, yeah.
Take the mic and
Oh yeah. This is-
All right. This is just an example. Some other graph. Okay.
Once you get back to C, you could have gone from F to F to G in the first place without taking a detour.
Yeah. See. The thing of it is that once you get, the reason this is not simple is because we have a C here and a C here, right? But what you can do is you can remove this, right?
I'll have to leave one of the C's.
And then you would have A, B, C, F, G. And we know that if this was possible on this graph, this was possible on this graph, right? And so this is simple. So, well, you'd have to generalize this.
Yeah.
It's a proof by example. It's not a proof by example. Okay. Okay, and now you guys, here is the definition of an Euler path, which is motivated by the Königsberg problem. Okay? Oh, by the way, do not pronounce this Euler, okay? Because it's Euler. That's the correct German pronunciation. And so this is called an Euler path. An Euler path of a multigraph is a path that contains each edge of the graph exactly once. Okay? And an Euler circuit is an Euler path whose first and last vertices are the same. So according to this definition, really what were the townspeople asking? Does an Euler circuit exist? Are you with me on this? And what did Euler prove? 19.8.
Even degrees.
An undirected, connected multigraph. Oh, we didn't talk about connected.
Is it only if every vertex has?
Has an Euler. What does IFF mean? If and only if. Every vertex has even degree. So if every vertex has even degree, then it has an Euler circuit, and if it has an Euler circuit, then every vertex has even degree.
So A would have to be
So we just added a couple bridges, we could do it.
One.
Well, and so look at this, what's the degree? 1, 2, 3, 4, 5. Oh, that has odd degree. So right there it tells you that there's, but here's 1, 2, 3. Oh, there's 3. Oh, they're all odd. 1, 2, 3, it's 3, 3, 3, and 5.
Between
D and C.
D and C.
Make it work.
If you added a bridge between D and C, that would make this even and this even. And A and B, another one between A and B, then you could do it. Now furthermore,
Let's build more bridges.
well, I mean, the bridges came first, the problem
They
came,
could take the bridge apart.
yeah. Or could you take away a bridge?
Or you could take.
You have to wait, take away two.
Yeah, but that'd be a hassle.
You take away, yeah, that's destructive.
You'd have to take
Or
away
you should just
two,
take
and then you wouldn't have one from A to B, and you have to cross that river sometime.
No, you could, couldn't you take away one of these and, oh no, you'd have to take away one of these.
You
Yeah.
have to take away one from A to
Well, there's lots of ways to do it.
B, and then the opposite way.
Okay, now, remember, what was that other theorem that we had? The number of, what was that previous theorem that we had? The number of, the number,
Vertices with odd degrees is even.
yeah, the number of vertices with odd, what if, so it's possible to have a graph with no odd degrees, right? It would have an Euler circuit. Are you with me?
No, I think
It would have an Euler circuit. Suppose that you had, now think about this. Suppose that you had a graph that had two vertices with odd degree.
that would just be one line.
My question is, would there be an Euler path?
No.
Yeah.
For that graph?
First and last would be the same.
That's not a circle.
No, that's not a circuit. That's why I said, would there be an Euler path?
Yeah.
Oh,
Means
right. Oh,
you
yeah,
can
yeah,
judge
yeah.
one.
Then there would be an Euler path, and it would have to and how would it have to be configured? It would have to start at one of the ones with the odd degree and do what? End at the other one with the odd degree. Because, I mean, after all, what happens is, if you're going a path and you go here, if you go into here and then out of here, you're using up two of the bridges. Right? And so as long as that's even, if you come in from one, you can leave from the other. But if it's odd and you come in from one, you might not be able to leave, because the other bridges might have been used up.
The bridges.
Yeah, you could use all the bridges if you started at one of the ones with the odd degree, and you ended with the other one that had the other odd degree.
Oh, what's the problem? To end at the same spot?
Well, I changed the problem when I said an Euler path as opposed to an Euler circuit.
The problem was Euler circuit.
That problem was Euler circuit. The problem I just posed was a different problem with an Euler path. Are you with
You can
me?
do the path.
Well, you
Start at C.
actually, I think if there's none of them with odd degree, I think it has to be a circuit. And the proof of 19.8 is in the book. All right,
Where's Königsberg at?
Where's the?
okay, Google it. Google it. I bet it's still around.
What's the connected bit?
Oh yeah, you know, we've kind of glossed over what it meant to be connected. Sorry about that. An undirected multigraph is connected if there is a path between any two vertices. So the question is this connected? The answer is yes, because no matter which pair you pick, there is a path between them. Now, if we had another, if on this graph we had another, this is A, B, C, D, if we had like an E here and an F here and a G here, and we had something like this, and this whole thing would not be connected. See, because even though there's a path between G and E and A, C, there's not a path between A and F.
For all BC type vertices.
Yeah, you could formalize, yeah.
Say there was a line between C and G.
If there would be but on the other hand, if there was a line, then this would be connected, because there'd be a path between all possible pairs. Are you with me?
So that one's not.
Correct, that one's not connected.
But if you took away A, it would be.
Right, that's right. Okay? So that's the definition of connected for a multigraph. A digraph is connected if making its edges undirected results in a connected multigraph.
It's in German.
What?
It's in the current Germany.
What part of Germany?
Yeah, you could Google Map, you could use Google Maps and then actually see a picture of it, I bet.
Yeah.
Oh, digraph is the one where it's pointed, right?
Can you explain part D?
Okay, so what you do is you erase the arrowheads and then say, is this connected?
Oh, alright,
And the answer is no, because A is sitting out here by itself.
got it.
Digraph means there's just the direct.
Digraph means the arrow, yeah, there's direction. Di means, that's a shorthand for directed graph. Digraph means
Are
directed graph.
multigraphs always undirected?
Yes. All right, now we have, actually,
You should leave early.
we should leave early. Now I'm going to erase this again and hope I don't have to redraw it. Now there's a couple more kinds of graphs that we have, and then 19 here, next slide. More definitions. 19.8.1 is the definition of a complete graph. All right. So let's take a look. So what is the definition of a complete graph? What does it say? A complete graph with end vertices denoted by k sub n is an undirected, okay, so undirected means what? No arrows. Okay. Loop free, so what is loop?
Point to itself?
Nothing goes to itself. Graph in which there is an edge between every pair of distinct vertices. So I'm going to give you K1 is this graph. K2 is this graph. K3 is this graph. K4 is what looks like what?
Either a square or a diamond or rhombus.
And then what do we have? Boom, boom, boom. See it, one from this one to all the other ones, one from this one to all the other ones, and one from this one to all the other ones. So everybody see that's K4? And what does K5 look like?
Okay, it's a pentagon. There's a line everywhere.
Lines everywhere. Okay, so let's do them systematically. One, so this is K5, right? Now watch this. 1, 2, 3, 4. Are you with me?
Yeah.
And this one is what? 5, 6, 7, 8, 9, 10. The question is, how many edges are there
The addition
in
of
K
the
sub n?
diamond. It's,
Yeah, you should be able to figure that out.
It's,
Let's take a look at I'll let you think about
it's
that.
n minus 1.
You might want to pause this on the video. Now let's take a look at the definition of a bipartite graph. This is a complete graph, so this is this is part A.
I already got it.
Okay, a bipartite graph. Now what does a bipartite graph look like? A bipartite graph is an undirected graph in which the set of vertices are partitioned. Now what's a partition? What's a partition? No, that's a relation.
It's a subset. Pairwise disjoint.
It's pairwise disjoint.
What is
And pairwise, that's one part of the
that? Is it like a
definition.
subset or something?
It's a set of sets.
A set of sets where none of them overlap. Oh, where the
The union-
intersection equals zero and
the-
the unions equal the universe.
Yes, okay. So here's an example of a bipartite graph.
So now
Let's suppose we have A, B, C. Now, in which the set of vertices are partitioned into two sets x and y such that each edge is incident on one vertex in x and one vertex in y. So let's say that this is A, B, C, A, B, C, and this is D, and this is E, and let's say this one is F, all right? These set of vertices are partitioned in such that each edge is incident on one vertex in x and one vertex in y. So check this out. Boom, 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 boom.
Let him get it.
This is a bipartite graph. This is a bipartite graph.
Even though F's just hanging out there.
Yeah, because what are the two? So what could a possible partition be? Okay, so let's say one possible partition.
Well, you can put F wherever you want it to be.
Yeah, that's why. One possible partition is x. See, the x and y are partitioned, right? So are subsets, right? Two sets, x and y. Okay, so one possible partition is x is the set what?
ABC.
A, B, C. Yeah, okay, A, B, C, F. And the other and then y would be
DE.
D, E. All right. Another possible partition would be what?
A, B, C, D, F.
Mhm. And that definition would still hold.
What is the other two options?
Mm-hmm.
I don't get it.
There might be other options, but I'm trying to find them.
So one of them in X has to be connected to all the ones in Y?
No, not all.
No. Just some. It's not connected to anything within the partition.
Just means each edge is only.
There's not an edge from C to E.
There's no edge from
Just
X
means
to E.
each edge is only used once within each partition.
Wait, what?
It's not a multigraph.
If there was a,
It's not a multigraph. It's an undirected graph.
Right.
So we,
if there was a line from D to E, you couldn't use D and E.
if there was a line from D to E, it would not be a bipartite graph.
So basically, like,
Bi means two. Right? So there's
two partitions.
there's one partition, there's two sets. The partition is the, okay?
But you can't be connected to anything within the partition.
Right. Every edge goes from something in one to something, to an edge, from a vertex in one set to a vertex in the other
F
set.
doesn't.
So F can be wherever you want.
Can C go to E then?
Well, this is one possible partition, this is another possible partition. C could go, there could be an edge from C to E, and this would still be a bipartite graph.
F doesn't go to anything.
But there could not be one from A to C. If there was one from A to C, then that wouldn't be,
Right, because it'd be within its own.
all right?
Why?
Every point
F isn't connected to something in the other set.
Every vertex doesn't have to be used, but every edge
Right.
that's there has to have that property.
Yes. Yes.
Every edge connects something that's in both.
Yeah, it says.
So confusing.
Well, no, it's precise.
I don't even know
Such
what
that each
means.
an edge incident on, here, this edge is incident on this vertex, and this edge is incident on that vertex. You're right, we did not, you're right, we did not define incident.
You should define
We did not define incidents. All right?
We should do that.
And here, a connected graph is bipartite if and only if every cycle has even length. Ooh, that's an interesting theorem. So put that in your pipe and smoke it. And with that, well, I'll see you on Monday.